Hey Algebra 2, here are the notes for 13.6 with exact trig values and periodic functions. So throughout this section, radian man will come in handy. So we're going to start by talking about that radian circle. The unit circle with radian man. So how does it help us find exact values? Well, if we read the key concept here, it says if the terminal side of an angle theta is in standard position and it intersects the unit circle at a specific point, then cosine of theta is x and sine of theta is y. So therefore, if we have a point, we don't necessarily need an angle in order to be able to determine the trig functions. So let's take the example of 150 degrees. If this is a 150 degree angle, that means we have a 30 degree reference angle. And based on what we know about 30, 60, 90 triangles, we know that opposite of 30 is going to be, is going to be the 1. But in this case, because we have a 1 as our radius here, this is actually going to be 1/2. And then cosine will end up being root 3 over 2. So if we talk about the point that this is at, we would technically say this is p of root 3 over 2 because that's the x distance it took us to get here, and then comma 1/2 because that's the y distance it took us to get up to that point. So if we have the point, we can also say cosine of theta, or a 30 degree angle, our reference angle for the original 150 degrees, is going to be root 3 over 2, and sine of theta is going to be 1/2. So let's look at this a little bit more when we don't have the unit circle. If theta is an angle in standard position and the given point P is located on the terminal side of theta at the unit circle, we need to find sine and cosine. Well, since we know that cosine is our x, we immediately know cosine of theta is negative root 3 over 2. Oops, I should go back and fix that here. This is negative because we went in the negative direction. Sorry about that. We then also know sine of theta because it's just the y value of our point. So in this case, sine of theta is going to be 1/2. We can do the same thing with non-unit circle points by saying the cosine of theta is still our x value of 3/5, and our sine of theta is still our y value with negative 4/5. So now let's use radian man to find the exact values, aka the ones with those square root symbols, no decimals, of the following numbers. So the first one we have here is cosine of 2,880 degrees. Now, 2,880 degrees is not in our unit circle, so we need to find a value between 0 and 360 degrees that has the same terminal side, but has a different angle measure. If you remember from last semester, at the very end there, we talked about these, and I told you they were called coterminal angles. So that's what we're going to do now. I do that by taking my degree symbol, I divide it by 360. This tells me how many full laps my angle made around the circle. So if I actually graph this on my unit circle, it says I started here and I made 8 full rotations. This means that a coterminal angle to 2,880 degrees is just 0 degrees. If I go over and I grab radian man and I look at my 0 degrees, I know this is hard to see because these values aren't very bright, but if you look here, my cosine is just the value of 1. So when I go back over, I know the cosine of 0 degrees is 1, so therefore the cosine value of 2,880 is also 1. For our next one, we have sine of negative 510 degrees. Trying to see if this helps us at all. It does a little bit. So sine of 510 degrees, if we look here, is again not between 0 and 360. So what I'm going to do to find a coterminal angle is I'm going to say 510 divided by 360. That says I have 1 full lap, which means I have 510 plus, would be negative 510, plus 360 is negative 150. That is between 0 and 360. So when I graph that, it's going to be right about here. Again, negative means we go down first. It gives me a reference angle of 30 degrees. So when I go over here to my radian man and I look at the angle that gives me a reference of 30 degrees, it says I want sine of that value. So I'm going to find sine of whatever number is there. In this case, it is negative 1/2. So my final answer there is going to be negative 1/2. All right, next one happens to be in radians. And this one is actually really nice because it's on our unit circle. So what I do here is I go over and I look for 3 pi over 4 in radians. As I go up, I find it right here. Now, if I want sine of this angle, I'm going to find my y value, and in this case, it is root 2 over 2. You can see why having radian man nearby is really helpful because most of our values we can find just by looking at him directly. All right, the last one is cosine of 7 pi. So if I look at radian man here, I know that it takes 2 full pi to go around the circle. If I need 7 of those, I'm going to need to go around a few times. So I'm going to do 2 pi, 4 pi, 6 pi, and then another full one would give me 8. So I only go halfway, which means cosine of 7 pi has a coterminal angle of cosine pi. And cosine of pi happens to be negative 1. So when I look at my radian man, I can immediately see that negative 1 is my answer there. All right, most of that should have been a little bit of review from last semester. Let's jump into this new stuff now. So now we're going to talk about our graph of sine and cosine. And these can be a little confusing, but I'm going to try and do some highlighting to explain why this is the case. So here's our unit circle, or what a very egg-shaped unit circle looks like. Now, if I graph what happens over time with this circle, what is created is the graph of sine here. Now, how does that happen? Well, if I start at this point where we usually start on our unit circle, over time, I'm going to trace this line. What direction am I going? Well, I'm going up. So you'll notice if I also start at 0 here and trace over time, my graph goes up until it gets to a certain point. That certain point happens to be the very top of my circle. And that makes sense because the maximum value of my circle, the topmost point, is also the maximum value of my graph. Now, as I keep going, instead of continuing to go up, now I start to go down on my circle. So after I've reached the maximum on my graph, I'm going to start to go down. Now, I eventually hit a point right here where I return to the x-axis where I started. You'll notice whenever my unit circle intersects the x-axis, so does this graph. So where I have a 0 on my unit circle, I also have a 0 on my graph. But when I get to that 0, I don't suddenly pop back up and start going upwards. I continue going downwards, which is what you see on this graph. I keep going down. Now, I go down until I reach another important point. I reach the minimum of my unit circle, which also happens to be the minimum of my graph. Once I reach that, you can see my direction changes again and I start to go up in the positive direction, which is what happens here again. I start to go up. Now you'll notice as I go back up, I reach my original starting point and my 0 of my graph. Now you'll notice if I then go around the circle again, the same exact graph will occur. This is what we call a periodic function. It means that our function over time is going to repeat. And a period is the time it takes for a graph to repeat itself. So I'll write that down for you here. Period. time it takes for a graph to repeat itself. So the period, or the time it takes for a graph to repeat itself in terms of the unit circle, is actually 2 pi, because we start at 0 and the time it takes to get all the way back around is going to be 2 pi. You'll find the exact same instance for cosine. The only difference is it's shifted just slightly. So if we look at some different types of graphs, they may not be as easy with the unit circle. So what we're going to do to solve these is we're going to use something called the 5-point method. 5-point method. All right. The 5-point method says you're going to start wherever your graph starts, and you're going to find 5 important points for your periodic function. So in this case, let's follow our graph and see what happens. My first important point is a 0. As I follow my graph, I reach a maximum. That's an important point, just like it was on our graph up here. I follow continuously, I hit a 0. That's an important point. Keep following, I hit a minimum. Keep following, I hit a 0. Now, if I cut this off right here and I continue to look, I should see that exact shape repeated, showing me that this is a periodic function. And the distance from one stop to the next stop is the length of my period. So the distance from 0 to 10 tells me I have a period of 10. Let's do the same thing with this graph. We start at our 0. We go up. Now this one's a little tricky because if you go across, you have 2 points, but technically because you only reach the maximum value once, we're only counting it as one value. So this, I guess you could technically put a dot there to show you that it's a maximum. All right, keep going. We hit a 0. That would be our 3rd point. We keep going. Again, we only hit that minimum once, so that's our 4th point. We keep going, we hit a 0. So if I draw my little lines here, it shows me that the period starts at 0 and goes to 2, starts at 2 and goes to 4. So my period for the second graph is 2. All right, last one. As you ride a Ferris wheel, the height that you are above the ground varies periodically as a function of time. Consider the height of the center of the wheel to be the starting point. So even though we're used to getting on at the very bottom of a Ferris wheel here, in this case, we're actually going to graph it as if we're getting on here. A little weird, I know, but bear with me on that. So it says, a particular wheel has a diameter of 38 feet and travels at a rate of 4 revs per minute. So I'm going to just draw a little sketch here because I know that the whole thing is 38 feet. It means there's 19 feet on top, 19 feet on bottom of this. If 4 revs equals 1 minute, I want to find the period where it takes a certain amount of time to go 1 rev. Well, if this is a 4-to-1 ratio, it makes sense that this should also be a 4-to-1 ratio. And if we find 1/4 of a minute, we find that it is 15 seconds. So the period of this function is going to be 15 seconds. That helps me when I'm graphing my periodic function because if I go down here, I know that I should start at 0. That's when you first get on the Ferris wheel. And I should certainly end at 15 seconds based on the fact that I know it repeats every 15 seconds. And just like I did with the unit circle, I'm just going to trace this Ferris wheel's movement over time. So if I start here, I start by going up. When I reach a 1/4 of the way around the Ferris wheel, I start to change directions and go down. When I hit the midpoint, I continue to go down. And when I hit the 3/4 point, I start going back up. Because this is a unit circle, I know what this actual graph is going to look like. I just need to determine what these 3 points are. Well, I know at the halfway, I'm going to be 7.5 seconds in. 1/4 of the way and 3/4 of the way, I have to find that information. In this case, it's going to be believe it's 375 and 1125. And just like I did before, I go up until I reach that curve. I start to go down. I didn't space these out quite evenly, but you get the idea. I keep going down once I've reached that until I hit the minimum of my Ferris wheel. And then I start to go back up until I've reached my starting point. So just like we did before, this is a periodic function. And you could see that if we kept going around the Ferris wheel, this motion would continue and repeat with a period of 15 seconds. All right, that was a lot. If you have any questions, let me know.